So we want to consider derivatives and antiderivatives or integrals which involve working with our inverse trig functions, which we've just been considering. And so today we're going to think about derivatives of inverse trig functions, and then we'll think about antiderivatives that involve the inverse trig functions as well. We've got a whole lot of results on our, well, I shouldn't say a whole lot, there's a few results on our formula sheet that relate to that. So let's just go straight to those results there. The derivative of inverse sine, inverse cosine, and inverse tan. And we'll notice that those three are all expressed as the derivative of the inverse trig function of x over a. X over a. So we'll think about in our examples how we sort of get our expressions like that. But here we can see that the inverse or the derivatives of those are these expressions here. Now we're not expected to be able to demonstrate why that's the case. Really those are just results that we can take as given and we can sort of work with those. So there they are on our formula sheet. Let's think about, well in fact let's think about those but with some domains added as well. So here we are, I've written them out and I've added some domains, and these may initially seem a little bit surprising because we're saying that for this particular function, inverse sine of x over a, its derivative is defined for the domain negative a to a, but not inclusive of negative a and a. Now if you think about this function here in terms of a transformation of inverse sine of x, so the transformation of inverse sine of x that has occurred, well really, so I'm multiplying x by 1 over a inside the brackets there, inside those brackets. So that relates to a horizontal dilation by a factor of 1 over a, or a horizontal dilation by a factor of a. So if we were to look at the graph of, so this is sort of the graph of y equals inverse sine x, and what's happened is a horizontal dilation, so that instead of the domain now going from negative 1 to 1, it now goes from negative a to a. So that function itself is defined, the domain of inverse sine of x over a is certainly negative a to a inclusive. But the issue we've got with the derivative, well, you can see from this that if x is actually equal to a or negative a, then the denominator is going to be 0. So this is going to be 1 divided by 0, which is undefined. So for that reason, negative a and a. But even if we look at the graph, we can make sense of that by seeing that at x equals negative a and at x equals positive a, the slope of the function there is actually undefined. So the graph doesn't have a derivative defined at those points. Same for inverse cos x, so same domain there, but inverse tan x is defined for all real numbers, and its derivative likewise is defined for all real numbers. So this expression here is not undefined for any values of x. Alright, so let's actually maybe then sort of consider some examples, so working with these particular expressions here. So let's go to the exercise that we're going to be working here in 11b, and in this case we're trying to find the derivative of these particular functions. So let's start with something nice and easy. We've got the derivative d dx of inverse sine of x over 2, and so for that one we can see that our a value is clearly 2 when we're looking at this expression here, and so we can just substitute straight into there. So we can say, well, that's 1 over the square root of a squared, which is going to be 2 squared minus x squared, which is equal to 1 over the square root of 4 minus x squared. And that's going to be defined for all values of x between negative 2 and positive 2, not inclusive. Let's look at another slightly different one here, because we're going to have to be able to be a bit flexible here. So let's go inverse cosine of 2 times x. Now there's a couple of ways that we could go about this. one way is probably a little bit easier than the other, but both ways are sort of useful to have our head around. So one of the ways that we could go about this is to say, well, I can just rearrange that to make that x over a half, and then my a value there is clearly a half. And so using the, let's go dy dx, so using my result here for inverse cosine, I can say if I've got an expression in the form inverse cosine of x over a, then its derivative is going to be in that form there. So substituting in, I could say -1 over the square root of, and this has to be a squared, so it's going to be a half squared minus x squared. Now, if I want to make that a little bit neater, I sort of want to get the fraction out of the fraction there. And so on the denominator, I might say something like, well, let's say -1/2. We'll take that factor out so that I can say that denominator there is, this term here is 1 times a half squared, and this term here is going to be 4x squared times a half squared, isn't it? And just check that that makes sense, because a half squared is going to be a quarter, and a quarter times 4 is just going to give us the -1 coefficient there. And then I could take that half out of, so the square root of a half squared is just a half. And then I could say dividing by a half is the same as multiplying by 2. So there's a way that we could sort of express that, you know, a little bit more neatly without having fractions within fractions. Now, I reckon there's probably a slightly quicker and maybe easier way to understand that one, and that would be to use the chain rule. So let me do this as an or. We could say let y equal inverse cos of u, where u is equal to 2x. So therefore, dy du would be, well, applying the rule to inverse cos of u, it would be -1 over the square root of, well, u is really u over 1, so our a value would be 1, so 1 squared minus u squared, and du dx would be the derivative of 2x, which is just going to be 2, isn't it? So that's 2. So dy dx, let's put that on the next line so it fits in a bit better. Dy dx is equal to dy du times du dx. That's just our chain rule, isn't it? So dy du we said was -1 over the square root of 1 squared minus u squared, and du dx was 2. So that's -1 over the square root of 1 minus, and u we said was 2x. Sorry, I should have multiplied by 2 there, shouldn't I? Let's change that and make that -2. And so that would be -2 over 1 minus 4x squared. Now, the way I've written that, it's kind of taken, you know, probably a few more lines, because this was a bit bunched up in here. But I think in some ways the chain rule might actually be a little bit easier to apply, so we don't have to be working with those fractions in there. Having said that, when it comes to anti-differentiating, it might actually be useful that we sort of understand how we can use fractions in that particular way.